Welcome everybody, especially for those who just joined us. Thank you for coming. We would like to extend to you a very warm welcome to our third breakout session for the theme, the impact and consequences of technology. I'm Marvin Wall. I'm a language assessment consultant for the British Council, and I'll be your host for this session. With me today is my colleague Chris Horn, who will be our co-host. Before I introduce our presenter today, I'd like to remind you to please keep your microphones muted. We will also be recording this presentation and uploading it to our lobby platform later today. And if you have any questions during the presentation, please leave a message in the chat box and we will address them after the presentation. Without further ado, let me introduce our presenter, Trevor Breakspear. Trevor has 18 years of teaching and training experience within the Chinese ESL and EAP context, and over 10 years of project management experience in assessment and localization fields. Trevor works in an innovations role within the British Council's East Asia Assessment Solution Team, currently leading on the academic development of new AI-rated scoring assessment tools, as well as coordinating and presenting academic and stakeholder research into new test concepts, leveraging both AI and human raters. He's currently completing an MA in language testing at Lancaster University. So with that, I'd like to hand over to Trevor for today's presentation. Over to you, Trevor.
Thanks very much, Marvin. It's the worst thing you can possibly see at the beginning of a presentation. It's just telling me my internet connection is unstable, which is even more embarrassing as I'm talking about tech today. So if I do disappear, please do bear with me. Yes, as Marvin says, I've been lucky enough to be involved in the development of some new product concepts involving the use of auto rating. And today I want to give an overview of a work in progress validation of a pronunciation auto-rater. So it basically provides scores and feedback. This is particularly for the word level. So today I want to sort of, first of all, introduce the main purpose of this research. So we want to understand the efficacy of the pronunciation scores given by the machine through an AI system. To put this in context, this is word level only. So we're looking at segmental pronunciation features. This is for a low stakes AI rated classroom assessment to be used in a formative context. I think actually Luke mentioned this in his plenary. I mean, one of the challenges in developing AI technology driven solutions in assessment is the idea that we need to be collaborating in a cross-disciplinary way. And I hope today I can show that I'm not from a tech background, but even so, as assessors, as teachers, we can engage with tech partners to sort of achieve this bridge. And hopefully I can show that we've been able to give meaningful feedback on the weaknesses of the system to improve auto rating. I'm going to kind of take you on a journey of our research design, and it's not a complicated research design. Again, I think it's something that can be easily replicated. It's something which we hope, in terms of insights, will sort of give you some ideas on how we can actually engage with the technology. So I'm going to take you on a quick journey of these steps, and then we'll finish with some, maybe probably the most important, what we're going to do next and how we're going to continue to validate.
Sorry, Trevor, let me just interrupt if I may.
Please.
The audio recording, audio volume goes up and down. Maybe you could speak closer to the microphone. Just maybe that might help.
Hello, I didn't hear that, Marvin, sorry.
Sorry, if you don't mind, maybe you could speak closer to the microphone because the volume goes up and down.
Okay, I think it's a connection problem, Marvin, but I will try and speak louder. I do apologize that the connection today is not great. Okay, as I was saying, the key focus is to look at data that's provided to students, so feedback and scores. And to give you a bit of context, what we're looking at is a part of the product where the learner records a word after they've recorded that word, they are given feedback and certain data. And I'm just mocking up this data on these slides here. So first of all, they're given a score out of 100. So in this instance, the student has recorded the word character and given a score of 45. We then look at data separated into what we call work required or highlights. Work required would refer to a performance that is perhaps needing improvement. So it does not necessarily conform to the various forms of native pronunciation and non-native pronunciation. We'll talk about that a bit later. And obviously work is required to improve that performance. A highlight would be an example of pronunciation which the machine feels is accurate, at least in accordance to the various acoustic models on which it's trained from the different accents and native speech. An error category, which is a word stress error or a phonetic accuracy error. So it's telling our learners about the type of error they're making, not just that there's a problem. And finally, there's the option to actually listen to your recording, the learner recording, and compare that with a model recording. So this is the data that's given, and this is what we wanted to evaluate and validate. So how do we do this? Well, the first thing, obviously, is we needed to compare human ratings and machine ratings in order to see how accurate the machine was. In order to do that, to start with, we needed to develop a rating scale that the human raters would use in order to make that comparison. We actually started with a 3-scale band, and we found that it was a big problem because most of the raters were actually rating at band 2 out of 3, and we weren't able to discriminate the range of performances that we were getting. So we then developed a 5-band scale, and we found that this was better to discriminate the data that we were given. We wanted to develop a scale that was easy to use, clear, concise, and discrete. And when we say discrete, we were aiming for bands to discriminate between performances quite simply, so that the judgments were easier to make. The scale was based on 3 features. So phoneme accuracy, and you can see here that we're looking at the top, reflective of various native speaker samples, and at the bottom it will be mispronounced. You have some substitution or deleted phonemes, for example. Secondly, we were looking at word stress, and obviously at the top, correct syllable placement, and at the bottom, stress may be faulty. We looked at these really because these were the features that the machine was using to rate. So we're looking in a quite simple way to match and map the features of the auto rater with the features of the human rater. And this is very problematic. I'll talk about that later. And finally, we were looking at comprehensibility. So at the bottom of the scale here, we're saying that perhaps there are issues with comprehensibility that are affected by both phoneme, and stress patterns. Before we went to the live rating, we also conducted a rater perception survey to see how easy it was for raters to actually use this tool to discriminate performance, and it was fairly positive, so 4.23 out of 5 average supporting that use. In the end, we used 5 raters to rate the performance of every sample that was rated by the machine. So we have quite a lot of data. Those examiners were experienced in ratings. We used Facet software in order to identify outliers. So this is data that, rating data that perhaps was less consistent, and we used that to retrain or give feedback to raters. We used what we call the fair average score. Without going into too much detail, this is the observed average, but then the software will calculate and modify the average based on rater trends and bias. So it's generally seen as a fairer average. In total, we had 280 word samples, 109 of which were work required, and 171 of which were highlights. This is the process we used. So we asked our raters to listen to the MP3 sample, to transcribe that sample. So they listened, write it down. Then they listened to the model answer, and then they gave their score. For me, this is actually one of the most interesting parts of the research, and we would like to do more on this. Because, and Luke also mentioned this, so the difference between focusing on comprehensibility and intelligibility is expressed within this process. So if you transcribe something, there is empirical evidence in front of the rater of judgment on a performance. Comprehensibility is subject to lots of subjective factors. And we felt by combining this, at least we were sort of tapping into both intelligibility and comprehensibility as well. And so at the end of the day, we asked the raters to complete a sheet. They transcribed their answers and they also gave their scores. Because obviously we have 5 raters, we can start sort of digging into the rater reliability. And this is obviously important. If we're comparing human ratings and machine ratings, we want to be as confident as we can in the human rater reliability. I'm going to describe very briefly some of the concepts we've used. I'm not an expert in facets, but maybe other people aren't either. So very briefly, I'll talk about some of the concepts and then show you the data that we came up with. So this, basically the three main aspects we were looking at was separation, and this is expressed in terms of linear rating arguments. So let's have a look at what that could look like in a fictional example. Here we have an example of say 10 candidates, a score of between 0 and 12. This is just a fictional example. So we've got rater 1 here. If we add rater 2, if we look at the principles again, rater 1 is slightly more severe. So rater 2, when we look at candidate 4, there's exact agreement there. Let's add another rater there. So this rater again is more severe than the other 2, it's harsher. Rater 3 has no agreements with the fit statistics. So how well they fit together, watch the lines go up and down. It's actually quite close. So we've got quite good fit, even though the separation or the leniency and severity is slightly different and there are no exact matches. Let's add a final fictitious rater. Now this rater is a problem, quite frankly. We see there's a lack of fit. Sometimes they're the highest and sometimes the lowest of the sample. The fit stats aren't good. So in this example, we would be wanting to look at retraining the rater or perhaps not using their data for further development work. So let's have a look at the samples that we came up with then. So for our set, we can see on the left with the rater measurement statistics that the fair averages, and a fair average again here is the average score of each rater across the whole sample. So rater 1 was the most severe, the meanest rater, if you like, at 3.27. Rater 2 was the most generous at 4.115. So we did see a range of severity and leniency there. The infit statistics, so that's the idea of the correlation of the lines going up and down together. This generally, and the literature suggests, should fall between 0.5 and 1.5. And we can see here, generally that was the case. Perhaps rater 4 was a little bit close to the 0.5 there, but generally okay. In terms of agreements, we're looking at the expected. So the model thinks we should be agreeing 37% of the time. We actually saw agreements 33.1% of the time. That's a bit lower than we would like, to be honest. But if we consider this across the exact matches and within one band matches, in this data, I've shown the highest and lowest rate of reliability. We wouldn't normally do this. Normally we would go across. But I wanted to show examples because then we'll bring the human machine data in and you can see a comparison. So in this case, inter-rater reliability between raters 3 and 4 was around 90% at the highest. And at the lowest end, the correlations, I think between 1 and 2 were about 78% within one band. Let's bring the human machine correlation in then. And here we can see that actually the correlation sits between the highest human rate of reliability and the lowest. And again, this is looking at exact matches and within one band matches. of around 83, 84%, and that's for the whole 280 samples. When we break it down, it becomes a bit more interesting. So highlights, and these are the strong performances. So when we just compared reliability for the strong performances, we see a similar pattern. However, when we look at work required, we see actually that the reliability between the machine and the human is lower. And work required is about giving feedback to improve performance. And if we're giving feedback to improve performance that's incorrect, then that could have serious consequences on the use of the product. So we were obviously really concerned about that and wanted to dig into that data in a bit more detail. So how did we do it? Well, we wanted to identify the outliers to start with. So we looked at those samples that had the biggest difference between human and machine correlation. Sorry, the negative correlation, the biggest difference between human and machine scoring. So what we found was that there were certain words that tended to have the biggest variance between machine and human. Literature is particularly obvious here because there were 13 examples that contributed to a negative correlation. So we can be confident that there's a problem there. So what did we do? Well, this data we shared with our tech developer and asked them to basically have a look at the engine and the performance of the engine for these words, and then to obviously get back to us on their findings. So this was like a signpost, if you like, for us to sort of dig a bit deeper. And what we wanted to do particularly is focus on work required, as I mentioned earlier. Before I talk about that, there are two really important concepts that I just wanted to quickly mention. These are false positives and false negatives. So a false positive is a comment or feedback which is untrue. So in the case of the doctor here giving advice or saying to a man he's pregnant, that is a false positive. Equally, a false negative is a negative comment or a negative piece of feedback, which also is not true. So if you say to a pregnant lady she's not pregnant, that's incorrect. And the more interesting thing is what's the consequence of that? And which one is most consequential and potentially in a negative way? Well, the answer is false negative in this context. So a pregnant woman who is unaware she's pregnant may change her behavior in a way that endangers her child. That's quite dangerous. So if we bring it back to our context with false negatives and false negatives and positives, a positive would be a student who performs maybe not that well, but the machine will give them positive comments and may overrate their performance. So that would be a false positive. A false negative in our context would be a performance that was underrated, a performance where negative feedback was given when maybe it isn't justified. And again, if we link that to behavior, what that means is that perhaps when you receive that feedback as a learner, you will want to change your behavior. Even though your pronunciation is correct, you may want to change your pronunciation in order to satisfy the machine. And the consequence of that in the classroom could be quite negative. So we're very interested in exploring false negatives. I wanted to give you some examples of this from the data. And again, these are words that represent some of the biggest differences between the machine score and the human score. The word visit, for example, we asked a further researcher to listen again and to make comments on the performance, to basically analyze these outliers. For visit, we found that the machine score was underrating. So this is a false negative. The human rating was higher. It was marked as a work required. So there's something going on here. Why is the machine underrating this performance? Well, we looked at the comments from the researcher, and they said that it was an example of very strong performance, and it was UK received pronunciation. That's one thing they noticed as a result of listening to the sample. So we were thinking, is the machine able to recognize or able to score that kind of variant? So that was a question for us. Let's look at another example, also flagged as a work required. The word character was given a very high score by the machine, a 4.96, much higher than the human rating of 3.4. So this is a false positive where the machine is overinflating the score. However, the problem here is actually shown not just in the comments from the researcher, but also in the machine itself. The machine identifies stress as a problem. The human rater also identifies stress as a problem, saying that the second syllable is incorrectly stressed. Could be like something like character, perhaps, is coming through here. However, the machine score is not incorporating stress into the scoring criteria. What this means, and it is an insight for us, is that that score is very narrow construct. If we're looking at segmental level, we're probably talking about phoneme matching and not much else. So it gives us an insight, and it also is obviously a problem we need to address. So we wanted to give feedback to the tech supplier. Before we did that, we wanted to make sure that it wasn't isolated. So we went back through all the data to see whether this problem occurred more than once. And we found that actually it was prevalent. So for example, visit, page turner, and fiction were all examples of false negatives caused by perhaps the inability of the machine to accommodate UK English variant. The other issue we talked about, the false positive, which is 2 examples of character and easygoing. Again, the machine is not incorporating stress issues into the final score. So what did we suggest and what happened? So the recommendations from us to our tech supplier was go back through the dictionary, through your acoustic modeling to see whether there are any problems with these particular words, particularly with literature, as we saw it as a big problem. The second was to see whether UK variants had been incorporated into the engine design and was reflected in performance. And finally, to consider ways to incorporate word stress into the construct that was being measured within the final score. So what did the tech partner do? Well, first of all, they did actually identify a problem with literature, and it was actually an issue with the dictionary. So it was a very simple fix. Secondly, they did upgrade dictionary entries. They looked at their acoustic modeling to ensure that UK English variant was included. This was quite interesting. We sort of probed here and said, well, is it a question of one or the other? And they said, no, we can actually have more than one variant being represented within the data set at the same time, which is crucial because within our context in China, you have students who use US and UK and Chinese, obviously Chinese style pronunciations. So we need as broad a representation of accent as possible. And finally, they agreed to incorporate stress into the scoring model and to deduct points based on stress errors made. Okay, so what next? I think the first thing to say, this is the beginning of the validation process, really. And we see this, and I talked about this in the symposium, we see validation not as a linear progression, which is often reflected in the interpretive argument, but more as an iterative process. So we've got to go back, we've got to get more data, hopefully over a wider range of test takers and proficiencies to see how this new combined model's working. And in so doing, to validate the penalty mechanism across work required, so that the poorer performances and the stronger performances as identified by the machine. So that's the beginning of the validation stage for that. Secondly, at the moment, we're just looking at segmental pronunciation, but what is more exciting is to broaden this out into suprasegmental. And by doing that, we've got a broader construct of pronunciation. We're bringing in liaisons, so the linking between words, intonation, sentence stress. These are generally, in the literature, stated as being harder to measure by machine, and we're very interested to see how the machine performs. And finally, and I mentioned this earlier, we want to try and map more closely what the machine can measure and what the human can measure. And that really is basically aligning the features measured by the machine, a feature analysis, if you like, and seeing what can be extrapolated into the scoring rubrics or band descriptors. It's impossible to have a perfect match, but it's something we're very interested to push further into that area, if you like. I think finally, I'd just like to say, I hope that what I've demonstrated here is that you don't have to be tech experts or data scientists to engage in the process of model building for assessment in our field. And I think this tech is here to stay. We will see more and more examples of this technology. And I think it's our job really to engage and to further and improve the quality, particularly for classroom assessment, where we can actually have a positive impact. Thank you very much.
Thank you, Trevor. So now let's go to our Q&A session. So we have a question from William Bayliss. He asks, could the automated solution be used in different countries with different accents?
Yeah, I mean, that's a really good question. I think the problem obviously is that we call it in terms of garbage in and garbage out. And what we mean by that is that the results that you get from an autorater can only ever be as good as the quality of the data that goes into it. There has to be a correlation between the data, particularly the acoustic data modeling, and the target test demographic. In our context, almost all the samples were a combination of Chinese speakers and native speakers that were taken from China. So the idea that we could use this model and then take it to, I don't know, the US or take it to the Philippines is a very, very dangerous one, really, because we're not tapping into the unique characters of the test demographic. Ideally, and best practice, that absolutely you train the engine on the same data from the same test takers that or users that will be using the product. And that alignment is something that we need to look into. The other thing I mentioned in the presentation is that the models actually allow you to have more than one and to have several types of accent variant. And we should look at being as inclusive as possible. And I think, as Luke mentioned, we're talking about ELF now. We're talking about language as English as a lingua franca. And by doing so, we're talking about inclusivity, and machine learning has the potential to actually bring lots of accents together. The problem is it's expensive to do it, and there is less transparency often from providers on what they've done. But the technology potentially can support this. So I do actually see some positivity there, but it does need to be considered specifically in relation to the users and their needs.
Okay, thank you. So we have one more question from Lucy Adams. The question is, you said the machine recognized RP and received pronunciation in some US dialects, which about non-RP dialects in British English? Sorry, what about non-RP dialect in British English? Just bath and off.
Yeah, I mean, it's a really excellent question. To be honest, the two questions are really quite similar as far as we're concerned. If you don't sample the difference between bath and bath, there's no way you can distinguish those different accents within the scoring model, within the feedback. So again, you've got to decide what you want. And if the answer is that you want to be tapping into lots of different regional accents, then you've got to sample them and you've got to make sure they're represented in the data set. So it is the same thing. I think one of the interesting questions for the test developers really is exactly what they want to see as standard. When I was actually giving this presentation, the thing I find hardest to enunciate is what is correct pronunciation, right? It's you can't say what is correct. I think often it's about what's representative, what the context is. But again, I'm going to go back to the idea of ELF. We should be inclusive as possible. And if we can bring these accents together into one model, then I think there's some interesting potential for further research there.
Thank you, Trevor. And we do have one more question. In fact, maybe two more questions, but I'm afraid we're out of time. So maybe Trevor, if you like, you could just leave them a message on the chat box. But
absolutely fine.
We have to end this session. So Thank you very much. Just like to remind everybody that the next session will be about application of Android-based eRubrics app for peer and self-assessment in writing and translation courses. So we'll see you then. Thank you very much, Trevor, and for everyone for attending. Goodbye.
Thank you very much. Thank you.